Good morning, all. Happy to introduce the next speaker, Mr. K.P. Surampalli. He has completed MSc Chemistry in 1980, joined the National Chemical Laboratory, Pune, as a research project assistant in the project of synthesizing and characterization of polycarbonate sponsored by IPCL Baroda. Then he entered the foundry profession in 1990, joined the Shivaji Nagar Works, which is now called as Kirloskar Ferrous Limited, Solapur, Maharashtra, as a junior technical assistant. From then on, he has worked in various foundries from 1997 to 2000 in Jaiswal Nico, Nagpur. Then in earlier 2000, he has worked in Amitech India Limited as assistant manager and was responsible for establishing foundry process quality, metallurgical laboratory, and implementing ISO 9001. In 2007, he joined Shriram Foundry, Rudrapur, as a project manager to establish foundry processes and laboratories. In the same year, he has joined CM Smith and Sons, Ahmedabad, Gujarat, as deputy general manager to establish foundry process and streamlining the quality assurance. Then, from 2008 to 14, he has worked with Munjal Kiru Private Limited, where he has held various positions in setting up the metallurgical laboratory and developed quality standards for various OEMs like Honda, GM, Nissan Motors, Maruti Suzuki, etc. During this period, he has handled various projects involving various grades of grey and ductile and castings for different applications, including passenger cars. From 2014 to 15, he has worked as plant head in Kandelwal Industries Private Limited, and then he joined as unit head of Shivalik Engineering Industries, Bilai. Currently, he is working with Bhartia Group since 2016 as Vice President Technical. Also, notably, he is the author of the book Green Sand Principles and Practice, published by Shivaji University, Kolhapur, in IIF Kolhapur chapter and NCTS Pune, organized in 2023. So, now the stage is yours, sir.
Good morning, all Foundrymen and friends. This my subject is very big subject. It requires more than 2 hours to cover all the foundry defects. It is running. So, in 20 minutes, I can cover only 2 defects out of our many defects in the foundries. So, there are major 4 defects we can see in every day in the foundries. Those are, first is inclusion defect. Every day we can see that. Second is porosity or pinhole, blowhole problems. Then silica sand expansion related defects. Then defects due to metal penetration. So today, just I cover only 2 defects. First is inclusion defects. When we go to that analysis of that defect, first we need to understand any defects during analysis, we need to understand the mechanism. And where we Foundrymen always missing that mechanism. We need to understand the mechanism. Once we understand the mechanism, how the defect developed in the castings, then it is easy to control the defects. So here, how the inclusion defects will generate in the castings. The mechanism of the defect to fall or trap any sand particles or particles of the sand, lumps of the sand particles on the surface, sand to metal interface, then these defects will develop. So during molten metal filling in the mold, due to imbalance in the pressure, the air displacement from the mold cavity to atmosphere, the sand particle displaced, flush out from the mold surface and deposited on the other part of the surface of the mold. So what happens when you pour the liquid metal in the mold? So whatever the pressure inside the mold, that all the pressure should be displaced comfortably, because the air density is 0.001293 gram per cc, and against that metal density is 6.63. So that huge density of the metal going inside the mold. So during that time, the air should go very comfortably outside that. So for that purpose, we need to design the getting system, and we need to provide sufficient vents. So to enable that all the pressure should go out from the cavity during pouring. So this is the only story of within some seconds, maybe 20 seconds or for 15 seconds. During that time, that pressure should release. Otherwise, the defects will generate. So, why the process we need to understand that the process in that when we design the casting getting system, so we need to understand the quantity of the metal, sand to metal ratio and pressure developing inside that. So with the help of some modules or solid modules, we can understand that how the defects will generate. In some cases, that slag or dross entered in the mold generated due to turbulence. Turbulence, again the turbulence will generate inside the cavity. That is also, there is any gap or poor design system, getting system in the castings. So, summary, we need to say the summary is that the defects controlled by green sand process is up to only 20 to 30%. It's a platform only, but the 70% defects control will covered by your design system only. If your design is robustic, then the defects can be controlled. Okay. So the fishbone diagram is given. So there are so many parameters explained here. So that parameters we can understand and we can control that. The process control related to green sand, the process control, I will explain that next slide. So what are the major aspects we need to understand to control this defect? First is the friability. We need to control the friability of the sand. Friability of the sand, and we need to maintain enough temper water in the sand. Temper water means just enough water to maintain maximum, to achieve maximum GCS values. And for that purpose, we need to control your return sand system. Return sand, moisture should to be controlled and temperature also to be controlled. Moisture to be controlled at around 1.8 to 2.2%. And then second is avoid interrupted pouring. Sometimes in manual pouring, the pourer will pour sometimes and they will stop for seconds. Then that time also this inclusion defects will generate. Then avoid core crush. During that core setting or core mold, then this crush will takes place during core setting and then sand inclusion will develop. Then improve compaction. If poor compaction is there, when metal is pouring, that loose sand will flush out and it collect somewhere other place of the mold surface, and the defects will generate in the mold and metal interface. Then avoid to dilute high carbon content. Control and optimize too slow and too fast pouring. This is also very important. So it is also related to your design system. Too fast pouring means pouring rate very high and pouring rate very low. In this case also the defects will generate, because too fast pouring means we have a limited vents in the system, so the pressure is not released from the mold cavity. So then the turbulence will generate inside the mold. Then sand inclusion defects will generate. Then avoid or dilute high carbon content. So most of the times, what happened in the green sand system, we always put more and more carbon, and carbon always gives more, absorbs more moisture, as well as bentonite also. So carbon absorbs sometimes 40% of the moisture, and bentonite absorbs around 30-35% of the moisture. So this combination of these two we need to control. And low LOI. LOI means that the carbon content is also always good. Now add small quantity of fresh silica sand. This case is when in some foundries where cold box core they are using. Most of the times in cylinder block and head casting foundries, they are using around 1:1.2, 1.3, 1:1.2, 1.3 ratio. That huge quantity of cold box sand is influxes into the green sand system. In this case also, we need to add some fresh silica sand, a very fine silica sand, that will help to enhance the strength values. Then avoid prolonged holding of prepared molds. So sometimes in any breakdowns, that mold, prepared mold, if we keep that mold as it is and we pour that holding mold, then these defects will generate. Then ensure and improve efficiency of the green sand mixer. This is also an important aspect. The mixer quality, mixing efficiency also very important. If poor mixing efficiency is there, then the more moisture is required and more bentonite is required. More bentonite means more moisture means the steam generation, and then pressure increase, again it lands into the sand inclusion defects. Then 10th number, control of volatilization. In some foundries, there where that cores are not using, only green sand is recycled. In that case, volatilization process will take place. So that inversion of that silica will take place. In that case, we need to add some fresh silica sand to dilute that. Then work, ensure sufficient bentonite active clay content in green sand mixture. So bentonite quantity is just enough required to maintain the strength. The strength values are different in requirement of strength values different in different foundries, different processes. So that we need to optimize that minimum strength we need to maintain to get the good castings. So maximum strength means again maximum bentonite required and maximum moisture absorption is there, then defects will generate. Then 13, control on organic resins used, where some in some foundries means cold box resin, core. So there some excess resin will be, if you use that, then again more gas will generate. So that gas we cannot take out because there is a limitation in our system, that venting systems. That's why again pressure develop inside the mold, and then the turbulence will create, and again sand inclusion will come out. So use honeycomb filters. So most of the people are using that foam filter, ceramic foam filter. But instead of that, ceramic honeycomb filters are always good. We have tried so many places, results are positive. So in foam filters, there is some inclusions will come out when we pour the metal. And so the inclusions means metallic inclusions possible when we pour very low temperature at around 13 and 15 degrees Celsius. Avoid too coarse inoculants. Sometimes metal temperature is very low, but inoculants size is bigger, so that inoculant particles will not fuse in the liquid metal, so the inclusion defects will come out. Last, avoid high melting ferroalloys added. So high melting ferroalloys like ferromolis, but nowadays they are not using. Earlier days we used to add that ferromoly powder in the ladle, so that is also not good because it generates sometimes defects. These are some defects, different defects, inclusion defects, slag inclusion and sand drop, lustrous carbon defects, dross defects, and sand drops and sand inclusion, mold wash, mold cuts, inoculants and metallic inclusion. So more details available in my book. It is in detail it is explained. Second. So now porosity are round shiny voids. So this is pinhole, blowhole defects or porosity defects. Major defects are pinhole and blowhole defects, but shrinkage also counted as a porosity defects. So porosity are round shiny voids on the surface and subsurface of the castings formed due to entrapment of air or different dissolved gases in the liquid metal. So formation of porosity involves several mechanisms. Though the term porosity indicates the characteristic of being porous with either voids resulting from trapped air, gas, steam, or pores from shrinkage. Here we explain porosity related to the green sand molding process. So green sand molding process, these defects due to evolution of gases, steam from the molding mixture and in the melt during filling and after filling the molten metal in the molds. These are defects related to gas and steam trapped or precipitated after after being dissolved in the liquid metal. So some gases also dissolved when we during the melting process, like nitrogen and hydrogen gases. So these gases also, when after pouring, during solidification, these gases will trap at the end of the cold metal junction. So the porosity or blowhole, pinhole defects will generate. Now the gases dissolved in the melt before pouring and are resulting from interaction between the melt and thus after pouring, the mainly nitrogen fissures and hydrogen pinholes. So the porosity means apart from pinhole and blowhole, the other defect is fissure, porosity defects. Porosity defects generates mainly with the help of this nitrogen. Nitrogen gas is a typical gas. It solidifies when the cold metal end of the castings, means after pouring a cold junctions, there these defects will generate. And pinhole, hydrogen pinhole defects also the same. So some alloys, when the excess quantity is there in the liquid metal, then hydrogen pinhole also will take place. So we will see that one by one. So this is a Ishikawa diagram for these defects. All possible causes I have summarized here. Next. So now we will go that one by one. Avoid water addition. So pinhole defects and blowhole defects. Avoid water addition high above temper point of the green sand. Temper point is temper point plus 10% or 10 to 15%. Means temper point means the just enough water to get maximum GCS values in your green sand process. And don't use moist core or wet conditioned core. So that core, when you pour the liquid metal in the mold, the surface moisture will come out and will generate the defects, pinhole and blowhole defects. So oxidized elements. Some elements are typical elements which always critical to these defects. That is like aluminum in the melt must be kept strictly below 0.009%. And titanium, zinc and magnesium below 0.05%. This minimizes the reduction of moisture present in the green sand and the associated formation of hydrogen. So hydrogen formation, these elements will act like a catalyst to increase the steam, increase the gases like hydrogen. Control level of trace elements in the melt. I already told that aluminum level in the melt coming from ferrosilicon. Where it comes from? Ferrosilicon, magnesium. These are alloys, and some automotive steels also. These elements will come. Scrap, inoculants, nitrogen content from resin binders. Mostly the nitrogen content is coming from cold box resins and some coal powders and some carburizers. Avoid high pouring temperature. So here very important, very high temperature. Sometimes thin castings, maybe they will increase mostly up to 1440 temperature. So this high temperature always dissolved most of the gases in the liquid metal and it solidify when the metal is fused. So as high pouring temperature can decrease the solidification rate of the castings and enhance the solubility of the gases in the melt. So the nitrogen and hydrogen solubility decreases with decrease in temperature. So here we can see that these elements that are still dissolved in the liquid alloy and migrate to those area of the casting with the lowest cooling rates, means end of the pouring where the solid metal collect. So that area always the defects will arise. Provide cold metal bleeders, especially in big castings like cylinder block and housings, to remove the dissolved gases before precipitate in the casting matrix. This defects, one of the defect I have observed in KFIL, where one cylinder block castings and typical area, the defect is coming, nitrogen fissure defects. So we have seen that area, the cold bleeders are not sufficient. So once they increase the cold area, cold metal from the casting, the defect is vanished. Control on nitrogen level with the titanium. These two elements, we should balance that. Because titanium, most of the time titanium will come from this CRC steel scraps, and nitrogen coming from the resin. So both these elements we have to balance it. If that excess nitrogen, again it generates the defects. Skimming. So we have to remove the slag. Otherwise what happens, prior to pouring, we'll remove small slag inclusions that can react in the melt to form carbon monoxide gas. Carbon monoxide gas first evolve when you pour immediately. So that gas will react with the slag and generate the defects. Now feeding, gating system. I already explained that gating is very, very important, because most of the defects, poor gating system, poor design, most of the defects will generate this pinhole as well as sand inclusion defects. So design the gating system, ensure the filling to minimize the turbulence and prolonged contact between the melt and the mold and core, thus limiting the amount of transport to the liquid. So gases, we have to remove the gases, whatever the gases generating inside that. So that gases means enough venting system is required to control these gases and to remove the gases. Avoid excessive use of nitrogen-bearing organics. So already explained that nitrogen-bearing resins means cold box resins. These resins having more nitrogen percentage, it generates the defects. So nitrogen percentage, the threshold limits also given here. So then some adhesives or some coatings also release the nitrogen gases, and dilution of system sand with fresh silica sand. So when the excess level of these gases increases in the system sand, we need to add more fresh silica sand. So fresh silica sand we need to increase up to 10 to 15%, 15% of LMT, liquid metal poured in the mold. So that will dilute all these gases sometimes. So the maximum recommended nitrogen content in the return sand to generate the fissure defects is about 0.15% for small castings, and medium to heavy section casting 0.1% weight for heavy section castings. So to control and the clay levels in the prepared sand, high clay levels always more moisture. So when you increase the clay level, so clay to get the strength or to make the homogeneous sand and to achieve the desired compactability, we need to add more moisture. So clay levels more means again more moisture and generate the defects. So the correct and or sufficient venting is required to evacuation of the gases formed in the molding during pouring. So the thumb rule for the ratio of ingate area, venting area, at least 1:1.5 means the area is 100 mm of ingate area, then we need to at least maintain around 150 mm squared area. So to release the pressure inside the mold to control the defects. Appropriate permeability of the compact sand mixture by using at least 3 sieve distribution. This is one more aspect, important aspects we need to see that. So the sand, whatever we are using in the preparation of green sand, required at least 3 sieve distribution. Means the percentage retained at least more than 10% in at least 3 sieves. Next. Please. Hello. Oh, these are pinhole and blowhole defects as well as nitrogen fissure defects. So gases in cast iron liquid like this hydrogen gas, hydrogen pinholes, these are the hydrogen pinholes, and hydrogen pinholes, then big blowholes. Thank you. Next. This is my book. In details, most of the around 10 type of defects are there. So that defects are explained in this book. Thank you.
Thank you, sir. Now I call upon Mr. S.V. Ranganathan, past chairman of the IIF Chennai chapter, to present our traditional Angavastram and memento to our speaker.